Sure. Okay.
Let me double check. Yeah, so welcome everyone to the second joint SUR and statistics seminar. Today we're going to have Rahul Mazumder. Rahul graduated from Stanford in statistics. After that he did a postdoc at MIT before he was a faculty member at Columbia Statistics for several years. Then he returned to MIT, where he's now an assistant professor of statistics and operations research. He's done a lot of exciting work at the interface of statistics and optimization, and we are looking forward to an interesting talk. But before that, let's give him a warm welcome.
Okay, so thanks, Martin, for the introduction and the invitation. Thanks for all of you for being here. Thanks to all of you for being here. So I'll be talking about sparse multivariate statistics. You have probably seen these problems before. I mean, even probably in undergraduate classes. But I will try to revisit some of these basic problems using new approaches. And in the process, what I'll do is I'll try to encourage all of us to rethink some of the basic assumptions that we make when we essentially say that, okay, these problems are not doable. If you actually think about approaching these problems from a fresh perspective, it seems that there is much more than we can do about these problems that we, there is much more that we can actually do about these problems. So I'd like to give you a glimpse of some of these problems. Okay, so towards this end, I'll give a brief overview of the types of problems that I've been interested in, or the main philosophy that has been driving my research over the past 3 or 4 years or so. So it starts with the basic statement that many fundamental problems in statistics or data science, machine learning, applied math, or anything related to data analytics, fundamentally, the way in which we construct the problems, they are fundamentally discrete or non-convex. So think about clustering, think about classification, think about variable selection. All of these problems, the most basic way in which we can describe these problems are combinatorial objects. Now, in order to approach these problems, the wider statistics discipline or data science has actually made fantastic progress. And towards that end, at the interface of statistics and computation, continuous, especially convex optimization, continues to have a significant impact in all these problems. So people have been realizing that in order to come up with good algorithms for these problems, it's important to draw machinery from well understood branches of mathematical optimization, and in that context, continuous optimization has played a very crucial role. But in my opinion, I've seen that there are a lot of other areas in mathematical programming that have not been explored to the fullest extent. All right, so today's lecture is going to be essentially on how to use techniques from computational discrete optimization to think about approaching these problems. But over the recent past, I've been working with collaborators where for large-scale convex optimization problems, usually we use first-order methods, first-order convex optimization methods, right? But there are some very classic methods out there which are based on cutting plane methods, which essentially, if I talk to graduate students around me at the ORC, cutting plane methods, yes, we know cutting plane methods. It turns out that if you approach some of the difficult problems using cutting plane methods, you can get performance which is similar to first-order methods. All right, so it turns out that if you use these techniques, which are well grounded in mathematical optimization, then there are lots of insights that we can get out of these problems. Okay, so the question is, can we use these techniques not only to develop faster algorithms, but can we use these techniques to better understand statistics problems? All right, so for example, Martin today morning, he was talking about a problem in permutations. That's inherently a combinatorial object, but there is a lot of statistics going on as well about overfitting and all. So similarly, eventually we are building these techniques to better understand statistics problems. So we have to understand things about bias, variance, overfitting, etc. to make sense out of this. Some of the methods that I'll describe are going to work for very high signal to noise ratio problems. If you decrease to signal to noise ratio, the signal to noise ratio of the problems, the results can be catastrophic. It's probably better not to use these models than come up with a zero guess, a null model. All right, so Sparse learning with discrete optimization, but I'll put a crossover there, and I'll say that I'm not being really a Puritan over here. The methods that I'll use are not necessarily purely discrete optimization. It draws machinery from several aspects of optimization. So I'll say these are mathematical optimization. And over the past several years, I've been working on problems on robust statistics, subset selection, factor models. And all these problems inherently admit a non-convex description. And we'll see that some of these problems we can approach using these modern methods. Again, in today's talk, I'll focus on the subset selection problem. Unfortunately, I'm not going to talk about just one particular specific project. I'll talk about the way in which our understanding about this problem has evolved over the past several years. I'll talk about pros and cons of the different approaches, and then the way in which we are driving, we are executing the research in this in this direction. Okay, so to set the stage before we dive in, let me talk about the class of problems that I'll discuss today. This is the sparse regularization in linear models. I'm sure all of you have seen this, but still, just to make sure that we are on the same page as far as notations are concerned, we are looking at the linear model regime, where y, the response, belongs to an n-dimensional space, x is the model matrix, and what we want is we desire interpretable or parsimonious models with good prediction or variable selection properties. We have been studying this problem for several hundred years, literally, but this is still a fundamental problem. So I don't need a justification why I am solving these problems, and I want to explore the statistics and computational aspects of this. And these have many, many applications in modern and scientific industrial domains. I'll not bore you with the details. I'll take this as granted, and then let's move on. So best subsets, the problem that I'll focus on, the current state of the art, a few years back. We want, so this is essentially what we want. We want a sparse model with good data fidelity. If I just take that as a primitive, the most basic way to write down the problem, which probably even an undergraduate or a high school student is going to understand, is minimize least squares loss subject to number of non-zeros in beta less than equals to k. Okay, so very, very classical estimate in statistics. It has excellent statistical properties. Using modern methods, you can actually come up with prediction error and variable selection error guarantees. A lot of these results are already well known. There are monographs written on this topic, but I'd like to draw your attention to this object over here, which essentially talks about an upper bound on the risk. There are some universal constants that are hidden over here, but there is a sigma square k log p over n. There is, and the constants over here, so essentially the upper bound does not depend upon x. You give me any x, I'll get this bound. Okay?
And the conditions on x.
No conditions on x are needed. But you're right, I will need assumptions on x in the next slide. L0 beautifully doesn't need assumptions on x. Okay, but I'll get to what you're saying. Computationally, this is a difficult problem. So for example, the R packaging leaps n and p around 31, that's what it solves. And not surprisingly, you're advised to stay away from this problem. Don't even think about this problem. It's a sin thinking about the problem. So the question is that really the case? And that's kind of got us thinking about the problem. Can we use advanced methods in optimization to think about these problems? So what are the current? So the statistics literature, broadly speaking, has responded very nicely to approach this problem. And I'll give you a very, very brief overview. So in this context, Lasso or L1 regularization has been used a lot. In terms of computation, it is very, very well understood, thanks to the developments in convex optimization. There are very fast solvers out there. The theory is also very well understood, thanks to the fact that it can be written as the solution to a convex program. Now, when the theory goes, this is related to the point that you were mentioning, yes, there are upper bounds on x, and the upper bound over here, the simplest upper bound over here, depends upon a quantity gamma, 1 over gamma square. This quantity gamma does indeed depend upon x, okay? And especially the correlations among the columns on x, features in x, are strong. This guy, gamma, can be small, and this guy can blow up. Okay, that's a fact. It's well known. Sometimes we hide it, but it is there, and we'll see how it comes up. Now, to fix these methods, statistician, okay, but so I should also mention there are also lower bound arguments about this, written by Zhang et al. And yes, and Martin Wainwright and Jordan, there is a paper. They talk about these lower bounds. Essentially, these bounds are tight. So you also have a lower bound, which essentially says that if you get a k-sparse solution based on the lasso, you'll get a lower bound of this order. So essentially it says that you cannot get this bound. You just cannot, based on a lasso-based solution. All right, to fix these problems, non-convex methods had a good alternative, and many of us have been using non-convex methods. In my graduate student life, I developed a non-convex method which is known as SparseNet. But the fact is, these non-convex methods are a good alternative, but they lead to computational challenges. So what is our new approach over here? It essentially says, okay, can we think about ways of certifiably optimizing this? And the main workhorses to approach this problem are tools from different branches of mathematical optimization. We are not using only integer programming methods. One of the main techniques that we are using to approach this problem are tools from tools inspired from convex optimization. These are the methods which are inspired by first-order methods in optimization. So if you are familiar with proximal gradient type methods or iterative Hart thresholding, these are popular approaches to attack this problem. We'll use this as one component. But unfortunately, as I said, I'll have my engineering hat on, though I'm not really an engineer by training. But I will not be using a written one way of approaching the problem. It's going to have different dimensions to it. So we will use this, and on top of it, we will use computational techniques from integer programming. So we will bring these two things together in an interesting way to make progress towards solving this problem. All right, so why do I care about mixed integer optimization? First of all, I mean, these are very well-grounded methods in optimization with roots in mathematics. So these are not hacky algorithms, and we understand a lot about what is happening over here. So it's a mature subfield of mathematical optimization and provides a very, very rich framework of doing modeling and computation with objects which are non-convex. Worst case, these problems are NP hard. NP hardness is a good thing because, I mean, it always gives us an indication about how hard a problem is. But at times, we should also be a practitioner and think about the practical aspects of the problem. And then, even though it is NP hard, in the worst case, that does not necessarily mean that the problem cannot be solved. Okay? So researchers in integer programming, my colleagues, they are essentially saying, okay, if a problem is NP hard, challenge accepted. Let's think about solving these problems using these methods. And there have been significant improvements in software and algorithms over the past 10 years or so. So I'll give you a glimpse of how things have evolved over the past several years. So just if you think about algorithmic improvements, this is machine independent. We know computers are becoming fast, but this is machine independent speed up. So some of the major solvers out there, Cplex, IBM's solver, this has undergone a 29,000 speed up in these several years. Gurubi optimization has also undergone a speed up of around 48.7 times speed up over these several years, which roughly amounts to 2 times speed up every year. So as we speak, these algorithms are becoming faster and faster. So these are tools out there, sophisticated tools at our disposal, and we will see how to use these tools to help us better solve the statistics problems that we care about. This is taken from the Gurubi website, an instance of all the different components or some of the different components that are actually using these solvers out there. So the question is, all right, so if all these if there are all these people in OR, widely speaking, are using these methods, why not statistics? Let's think about whether we can use these methods to help us statisticians solve our statistics problems. All right, so there are different examples or classes of mixed integer optimization. There are classes which are known as mixed integer linear optimization. There are classes which are known as mixed integer second order conic optimization problems. These are essentially 2 classes which are tractable in the sense there are advanced methods out there that can be used to approach these problems. There are several commercial or non-commercial solvers. I used to use MATLAB a lot, and now I'm transitioning to Julia Jump because of several reasons. Now let's go into the approach. So how are we actually how are we actually solving the problem? How do we set it up as an integer programming problem? So this is what we do. This is a very, very basic formulation, and it's very easy to understand. I set up the least squares loss function. Big M, this is the big M, this is a value, say 10,000. Though 10,000 is not going to work well, but assume it's 10,000. Zi's are binary. And Zi essentially triggers, controls whether the beta I is going to be 0 or not. If Zi is 0, you can easily verify that beta I is going to be 0. If Zi is 1, then beta I in absolute value is going to be less than or equals to M. Okay, so it's unconstrained. So this is exactly a reformulation of the subselection problem. Of course, assuming there is a bound. All right, so why do I care about this? Because let's think about the evolution of this problem on a so-called, on a diabetes data set. So this is a real data set. All right, so this is a data set that has been studied in several places. And then with time, I'm using an off-the-shelf solver to solve this problem. Along time, you see that there are different aspects of the problem. There is an objective on the y-axis, which is essentially the objective of this guy. All these points over here are feasible as far as the upper bounds are concerned. So you see that there is a schematic picture which is an empirical observation, and it turns out that it holds in many, many applications, and that is as follows. With time, the objective value goes down, and then it hits the global minimum. By the way, we do not know that this is the global minimum. We only know that this is the global minimum via the lower bounds. All right? And this is the place where I say these math programming techniques out there are telling us, are giving us guidance. We know exactly at the end of 100 seconds how far we are from the optimum solution. So for example, at the end of 100 seconds, we know that the objective value cannot be lower than 0.70.
So what is P here
in this particular problem? P is, I think, around 64. Okay. It's a small problem. Okay, so this N is around a 300, something like that. Okay, but again, yes, you're right. So you're probably alluding to the fact that these lower bounds, depending upon the time, these lower bounds can evolve slowly, so on and so forth. Yes, there are advanced methods that can address that issue. But the fact is, I want to get a solution with 50% optimality guarantee. Okay? If you use heuristic methods, it's difficult to get it. You may get it, you have to make assumptions on your problem. But checking restricted isometry property, I mean, that's as hard as, probably more difficult than solving this problem. Okay, so there are issues out there. It's not, there is no free lunch. All right, so this is the framework, and this is why I like it in the sense it gives you certificates of optimality, and it helps you do many stuff with this framework. All right, so now let me give you a few key ideas related to the question that probably Martin is alluding to. These lower bounds, how do we improve them, etc., etc. These are difficult questions. These are important optimization aspects of the problem. So some of the key ideas to solve this problem. One of the ideas is you can rewrite this problem equivalently as a problem which is like this. All right. Now, what are these? These are essentially additional constraints on the problem. These are known as implied inequalities or cuts. So if you work on integer programming problems, these are going to be natural to you. These are used to get tighter lower bounds from the LP relaxations of the problems. And these are needed, actually. If you want to make these guys evolve faster, or if you want the whole algorithm to evolve faster, these are optimization considerations that needs to be done. There are some other aspects that can be done as well. Now, some of these methods actually use some recent developments in the optimization literature. Due to work done by Vielma and co-authors. These are papers in math programming. So this is one of the basic ideas that are used to scale this problem up. All right. So these nonlinear optimization problems are difficult to solve. So the main idea that is used is, let's think about solving these problems or approximately solving these problems by solving a sequence of mixed integer linear optimization problems. So what you do is you take this set, you look at the level set of this guy, and then you do a polyhedral outer approximation of this in a very, very structured way. And then there are ways by which you can add cuts using convex duality, and then you can improve these lower bounds. Okay, so these are methods that have to be used. Some of these methods are already implemented in new versions of Gurobi or Simplex, at least in some versions of it. Some of these methods actually can read some of these papers in math programming and implement it. These are ways to improve the lower bounds. All right, now let's in order to move on, let's try to summarize. What have we learned using this approach? What does it actually give us? When the signal to noise ratio is high, these approaches, I'll give you I'll show you results later on, but let me summarize. Best subsets lead to compact models, good prediction accuracy, as well as good variable selection properties. And the approach that I briefly mentioned before, this approach works for P around 1,000 or higher hundreds and N equals to 1,000 or smaller. There are two aspects to this. The joint approach that I discussed, it takes around 5 to 15 minutes depending upon the difficulty of the problem to get a good solution. And these solutions can actually be better than the solutions obtained by Lasso or forward stage, stepwise, etc., things like this, usual heuristics. And the certificates can actually take a longer time. Okay, that's the fact. That's essentially what we have understood from this. But still, compared to P equals to 31 that existed in the statistics literature, this is a huge. This is an improvement. This is a gap. Now the question is, I talked to some of my colleagues. They asked me, or collaborators. They tell me, okay, 1,000. I want to solve larger problems. And I want to solve them faster. 5 to 10 minutes is probably too large for me. Can I solve them faster and larger problems? That's a natural question to ask. Okay, some people need to solve larger problems faster. So in the next few minutes, I'll talk about a recent ongoing project. We haven't written the paper yet. I'm working on the draft of the paper. It essentially tries to develop very fast algorithms using ideas from integer programming as well as local combinatorial optimization to come up with heuristic solutions to this problem. You have to give up on global optimality because I do not know how to solve, for example, a problem with n equals to a few hundred and p equals to 1 million to global optimality. At the moment, I cannot do it. Okay? So we have to talk about relaxing the notion of global optimality and talk about notions of approximate optimality. And I'll also define what I mean by approximate optimality notions. So the algorithm is essentially based on coordinate descent. Yes, statisticians love coordinate descent, and this has been out there. Gauss-Seidel. And the core new idea that we are using is combinatorial local search heuristics. These are ideas that are used in the combinatorial optimization literature, but I haven't really seen this in use as much in statistics, the statistics parlance. And I'll describe to you how much it's curious how much improvement it leads to. And we define notions of approximate optimality. I'll definitely like to acknowledge the work of Amir Beck and Yonina Elder in the SciAm-Opt, where they actually introduced the idea of using combinatorial optimization in a rather implicit way, but we take that idea and then build upon it. There has been a series of other works in math of OR and SciOpt where this idea has been generalized.
So before you go on,
yes.
Give me an example where in a statistical set,
yes.
I will have n is 500 and 1 million,
Sorry?
1 million covariates.
An example?
Yeah.
Also.
Area?
So SNP data P is very large. These are the order of million. SNP, single nucleotide polymorphism.
1 million?
Yeah, it can be large. Okay, good. So there are experts over there. And actually 24,000, 40,000 is, and okay, 1 million. Look, so there are parts of it which are practically motivated. There are parts of it where we really like to see how far we can push.
I get the want to push the part, but the statistical piece is.
No, there are many applications where P is 10, 20, 30, 40,000, as well as 1 million. And also it's easy to blow it up. I mean, you start with a problem with P equals to 1,000, start putting in interactions. 1,000 square is how much? I don't know. It's a large number. So these are used. These are out there.
But there may be problems in which you have some structure to the X's.
Yes.
That you could exploit in these problems.
Absolutely. Yes, you can. You can. And that's actually a very important point. I'll not have.
It may be that each one represents like an indicator for a subset.
Absolutely. Yes. So these are structured variable selection problems. Yes, exactly. And as a matter of fact, so that's some of the work that I am working on. So yes, I mean, you can go crazy with these combinatorial descriptions with these problems. I mean, that's a place, the structured variable selection. I mean, I don't know. I mean, to me, they just scream IP structure. There's just combinatorial objects. Yes, you can do these problems. I mean, the problems that I'll discuss over here, they do not handle that.
Very generalized formulation.
There are generalized formulations to approach those problems. There are generalized formulations to approach those problems, and these are very, very richly structured objects. You need heavy machinery to approach that. So I'll not be.
Go ahead.
So yeah, I mean. Yeah, so there is. So for example, so let's talk about the interaction problem. So in an interaction, we talk about a structure which is known as hierarchical interaction. Am I making sense? Hierarchical, if an interaction between I and j is in the model, a non-zero coefficient, then I should get the main interactions in the model. Okay, so that's hierarchical. This structure is basic IP structure. I mean integer programming structure. It's a combinatorial structure. You can relax it, but these relaxations are, you may run into issues with that. So I would say yes, we get benefits with these simple structures. I agree these are simple structures, but in my opinion, from my viewpoint, I need to understand what is happening with the simple problems before I dive into the harder problems. Okay, so let's talk about the simple problem, our algorithmic approach in order to achieve this. So I'll throw in a bunch of definitions. So what I do is I define this function. This is what we hope to do, f of beta, which is defined as the sum of f of beta plus lambda 0 beta 0. Due to some reasons, technical reasons, I cannot look at the constraint version of the problem. I have to look at the Lagrangian version of the problem. F of beta, I throw in the least squares loss, I throw in beta, I throw in L1 norm of beta as well as the L2 square norm of beta. I'll justify essentially this justification we got from another project where we actually justify the use of these conditions. This regularization often helps in problems. Now, once we actually write down these formulations, now if you think about basic stationarity of these problems, we can define what is known as a coordinate-wise stationarity for this problem. And a coordinate-wise stationarity, essentially what it does is it takes this problem, fixes all the coordinates, leaves out the ith coordinate, fixes all the other guys, and then optimizes with respect to the ith coordinate. All right, so this is basic coordinate-wise optimality. And then beta I star, I say beta star is going to be a stationary point or a fixed point of this sequence of updates if beta I star satisfies the arc bin condition. Okay, so this is essentially coordinate descent. I can think about applying an algorithm. So this induces an algorithm. What is the algorithm? The algorithm is as follows. You have, say, 5,000 variables. You initialize all of them with 0. You take the first one. You hold all the other ones fixed. You optimize. Go to the next one. Then go to the third one. These are very basic algorithms, Gauss-Seidel algorithms, coordinate-wise. But my point is, I'll use these algorithms to define conditions for stationarity.
Could you define that to a set larger than 1?
Yes, that's essentially the meat of this paper, of this project. Yes, and actually that's the place where local combinatorial optimization comes in. That's the richness of the problem, I would say. And essentially, integer programming is going to come in over there. Now the question is, the next question, as you were asking, higher order stationary conditions. Can you do it? All right, so yes, we can, and that actually leads us to what is known as local combinatorial optimization. I'll talk about partial swaps, but you can talk about full swaps, etc. And how do I define it? I'd like to define it in the context of, you give me a point beta star, which satisfies this condition. And then on top of that, I define another thing. So let S be the support of beta star. All right, so beta star is coordinate-wise stationary. S is a support. And now let's define two sets, S1, which is a subset of S, S2, which is a subset of the remaining guy, of the complement. And I define beta star as the argmin of this object. So what is this? U of S is defined as, it essentially selects a subset of coefficients S1 from inside the support, and it adds something from outside the support, and it does a full minimization over these, actually, full minimization over the other guys. This actually should be S2. I made a mistake over here. And the partial swap S1 and S2 is defined as if this minimization actually leads to a decrease in the objective value, then you take this, otherwise you do not. And then this again defines for us a partial swap invariant of order k if for all S1 and S2 of size k, this condition holds true. The partial swap S1, S2, beta star leads to beta star. So essentially, okay, so if you don't want to get into the technical details, what this essentially means is you can actually extend the notion of coordinate-wise stationarity to higher order stationarity. What you have to do is you have to look outside the set and then optimize over it. So let's do it via an example, a picture. So this is my current stationary point, beta star. The red object over here denotes my support, and this object over here denotes the complement of the support. So S and S complement. So the math that I described in the previous slide in pictures is this. So I take this, I take an set S1 from inside and I take a set S2 from outside. Okay, this is arbitrary, S1 and S2. And then I swap. The guys which were over here, which were zeros, which were non-zeros, I start setting them to 0. And these guys, I start setting them to non-zero, and then I run my coordinate descent algorithm again. If I do it, then I'll get a new solution. Okay? And then what I do is I then apply my coordinate descent algorithm on top of it. This leads to a cyclical phenomenon. Okay? So this is a schematic picture, but it's trying to illustrate what is happening, the notion of higher order swaps. Now let's look at a few special cases. It looks like an intractable object, but some special cases are actually very simple. And actually, if you do the algebra over here, the updates are very, very simple. So input coordinate-wise minimum beta, where S is a support of beta, for every I in the support. So this is this. For every I in the support, you run an algorithm. You look outside. You find out the minimum of the objective function by knocking the guy out inside, outside. So if we knock this guy out of the support, and then we take an element from outside the support and optimize over the element outside the support. We do it for all elements outside the support, and then we look at the objective value. If the objective value actually leads to a decrease in the current objective value, then we update, otherwise we don't. Okay, so this is known as the partial swap. A version of this method actually was mentioned in the Beck and Elder paper, and that's where I said, that's the place where I got the inspiration from, because it's a very powerful idea, and it gave us the inspiration to generalize it. All right, now let's talk about a partial swaps of order k. For larger objects, larger sizes, you cannot really, so the one-dimensional object, this can actually be done very, very efficiently. You can exactly write down what the updates are, and I'll give you a brief glimpse of the timings, which is going to give you an idea about how fast these methods are. So as you move over to higher order swaps, this is a problem that you want to solve, and this can be equivalently written as an integer programming problem. The point is, this is not a massive scale integer programming problem. This is a tiny integer programming problem with size 3 or 4. That's much more tractable. Okay, and that's essentially, if this algorithm converges, we have proofs in the paper which talks about the convergence of the algorithm. It is essentially going to certify the following thing: you have reached a fixed order, you have reached a stationary point which satisfies this swap invariance. All right, so hierarchy of stationary conditions. So I'd like to give you an idea about what do we gain by defining these esoteric objects, if you may will. Directional stationarity was one of the earliest stationarity methods that were studied by Seng in a very early paper, and essentially this is one of the main papers that are cited in coordinate-wise optimization. All right. There is also iterative Hart thresholding, which is essentially a famous algorithm out there, which can be used popularly to approach this problem. All right. These are essentially generalizations of gradient descent. So I can look at the iterative Hart thresholding updates and define first order optimality conditions based on that. Coordinate-wise is the method that I just described, the very first one at a time coordinate descent. This is partial swap of order 1. I write down also there is a version called as full swap, which is essentially an added generalization where you are fully optimizing over the new set, and there is a partial swap of order k. This is a hierarchy. So this defines the largest class of stationary points. This one is second, so on and so forth, so on, and you go down. Now what I'd like to mention is, from a statistical viewpoint, when the problems become very, very hard, you start gaining a lot over here. All right? So the hardness, the statistical hardness of the problem is experienced by the algorithm as well. So we do not have any results at the moment which justifies what is happening, but empirically we have observed that this is what is happening. If your problem is simple, in the sense, if you have lots of samples and the pairwise correlations are not too high, you use all these methods, is going to work. You don't even have to go down. I mean, these methods are going to work very well. Now, if the problem becomes difficult, pairwise correlations are very, very high, the number of samples are not too large, and the problem makes sense from a statistical viewpoint, that is information theoretically, then these guys start playing, doing their job. You get a lot of objects. I mean, of course, I mean, over here is the global optimum solution, but
are you referring to the correlations of the estimates or the correlations of the x's?
Correlation of the x's. Yes.
How large can K?
I'll give you some examples.
Because
I'll give you some concrete examples. I'll give you some. We spent a lot of computational resources to get the picture. I'll give you some. All right, so there is a package. If you're interested, you can try it out. It's prepared by Hussein, my student. And what it does is essentially implements these algorithms for a class of problems like this. It's written in C++, and it has an R interface to this. Hussein wasn't really interested in doing the R interface, but I pushed him to do the R interface because many statisticians like to use the R interface. Anyway, so he's really a C++ kind of a guy. All right, so timings, seconds. Let's give you an idea. But okay, so I've essentially made up a story. Okay, that this is done. This is going to be fast. Can I actually demonstrate that it actually works on problems? So in order to do that, let's look at an example. I have taken a bunch of candidates, competitors. L0 CD is the first algorithm that I described. L0 one swap. This is just the one swap version. L1 is the famous GLMNet implementation of the Lasso. And MC+, this is a sparse net implementation. I'm sorry, I'm biased because as a graduate student, I created this MC+ method. And this is the method created by Hestiad, Friedman, and Tipshirani. And L0 and L0 CD, these are the algorithms that we created in our new proposal. These are the different sizes of the problems. P equals to 10,000, 24,000, etc. So we haven't gone up to 1 million, but these are some sizes. And these are the timings that you get. So essentially, let's see. So L0 CD for these problems, by the way, these are timings on a sequence of 100 lambda values. Okay, just the L0 problems, so it's a polarization path. You take different sparsity levels and solve it on a path. That's how L1 works and these other methods work. So you see, the point over here is we see that there are some timings. If you look at this timings versus the L1 timings, so one of the comments that we make is, why will I use L0 methods? Because L1 methods are super fast. Now, if you actually think very hard about how to design algorithms and what is actually driving L1 to be very fast, you can actually give L0 the same intelligence. So yes, you can. I mean, this took a lot of time to do. I mean, it took a lot of time to do. The point is not that we get numbers which are faster than L1. They solve different problems. But the point is, if you're thinking of using these methods, and if you want to try a quick method to get an idea whether these work or not, they'll give you an idea, and you don't have to. These are two specific instances of data sets. Okay. They are different runs on the machine. These are synthetic data sets. So over here, they are averaged. That was all about the timings. All right. Now, as statisticians, let's think about, from a statistical viewpoint, what is actually happening. Do we actually gain or not? High SNR problems. I need to separate these two cases. High signal to noise ratio, where there is a lot of signal in the problem. Let's see what we can do. All right, so this is an example where you have n equals to 50, p equals to 2000. These are our different methods. There are different signal to noise ratio problems, 3, 7, and 10. We have the Lasso over here. This is the optimum prediction accuracy based on a validation set that is usually done. Validation set is used to choose the tuning parameter. And you see, these are the methods, Lasso, first order plus MIO. MIO cannot solve the problem to global optimality at this scale, but we use a first order method as well as the MIO, both of them together. First order method is essentially the heuristic. This is the iterative Hart thresholding heuristic, and SparseNet is essentially a very an algorithm that I did during my thesis, which solves approximately the MC plus penalized problem. What do I see? In terms of prediction accuracy, this one, which is the MIO, this one actually works pretty well. This is a case where X is drawn from IID Gaussian. X is IID Gaussian, but the fact that n is much smaller than p induces sample correlations. Okay, so this is a correlated example. Now let's see what happens in the sparsity. This is a place where there is a real difference. So if we use Lasso as a variable selection, what actually happens is Lasso brings in many non-zero coefficients. It doesn't really do variable selection as such, because it leads to a dense model, and you see it is reflected. So over here, n is 50, the number of non-zeros that you get are roughly around 40. So Lasso, in order to get a model with good prediction accuracy, it throws in a lot of coefficients with shrunken coefficients. all right? It shrinks them. That's what the L1 norm does. And that's why the sparsity is so high. But in terms of L0, you see that some number of sparsity is tiny, and it's comparable to the number of non-zeros in the underlying generating model. This is a synthetic data set. Okay. Now let's see what happens, the sensitivity to samples. Because honestly, this example was just one data point, one data set, one choice of n, one choice of p, etc., etc. Let's see what happens if you go on changing the samples. So these are the algorithms where the new algorithms that I described, the swaps, etc., they are being illustrated. So this is a problem where there is exponential correlation. That is, the correlation between xi and xj is actually rho to the power absolute I minus j. So this is the AR model that people like. So expectation, so the correlation between xi and xj is essentially rho to the power I minus j. And this rho object over here is essentially 0.9. So this is a case, this is a population setup. This is a case which people often say is easy for the lasso, but let's see if it is easy for the lasso. So P is 1000 and the number of samples are changing. This is a place where the problem is very hard statistically. You don't have enough samples. The signal to noise ratio over here is 10. Still, I'll say this is a high signal to noise ratio regime. Look at this object, this one. This is the probability of full recovery. So you run it for 50 times, and then you see for each of these replications, for each of these simulations, are you getting exactly the correct support or not? Okay, so this is variable selection. Okay. So L1 is 0. I mean, L1 is in this particular example, it does never select the right variables. It never gets the correct support. This is a version which is L0 swaps. This is essentially the one swap version of the algorithm that I described. L0, L2, there is also a ridge regularization that I have. L0, L2 swaps, and you see as a number of samples is slightly large. This is a place nothing is possible. I mean, this is a place where information theoretically, I mean, you don't have enough signal to recover anything. You go on increasing the number of samples, the probability increases, and then it goes to 1. Now, this is a place where when I was mentioning that if you use simple algorithms to solve these problems, like coordinate-wise minima, which was essentially very up in the hierarchy, the quality of solutions are not that good, and that is reflected in the statistics of the problem. This is L0. You see, it doesn't really select the right variables. So this is the price. This is the additional benefit that you get by solving by doing a good job in optimizing the problem. Okay, so. And this is the value added by using local combinatorial ideas from statistics. No, I don't know. I cannot, no, it's not. I cannot solve this problem. It's going to take days for me to run this. And this whole graph is generated in a few minutes. I don't know. So, okay, there are other methods as well. Stepwise. Stepwise actually takes long to solve problems. The scale of problems that we are talking about, stepwise starts becoming slow. Okay, and we are talking about real low-level C++ implementation. That I didn't do, who sent it, but he knows what he's doing.
Forward stepwise.
Forward stepwise is an algorithm which people think is fast, but when the problem becomes tough, when P becomes large, forward stepwise starts becoming very slow for reasons which are clear to understand.
Answer from the backward one.
They do not have even an answer from the backward one, even moving up, because of the way in which the choice.
P equal to 1000.
Oh, yeah, P equals 1000 is not, yeah, but it's not, right, sure, but yeah, that's correct, that's correct, that's true. But I showed you the timings a few slides back. Okay, so that's give you an idea. Milliseconds over here. Look, I'm not a particularly big fan of timings, right? Because different applications need algorithms which are fast. Some other applications they can wait for overnight. I talk to different people, they say different things. I understand that there are some people need algorithms to be fast, some people need algorithms to be slow. Not need, but depending upon the needs and the type of accuracy that you need, there are different ways to approach the problem.
A lot of these concepts don't have to be related to just the simple linear model that you started off with.
That's correct.
Much more complex.
Absolutely. That's correct. That's true. That's true. So, right, exactly. So, if you write down the linear, so if you think about it philosophically, right, linear models are subset selection. The way in which I write it down, the model doesn't have to be linear. The best linear approximation to the data, etc. But yeah, I agree. I agree with you. All right. Now, this is a case where we're looking at prediction accuracy. In terms of prediction accuracy, what happens is L1, L2 also leads to very good statistical, very good best prediction accuracy. If you increase the number of samples, then they start getting merged together. Okay, so by L0 over here, I mean L0 CD. So you're approximately trying to solve the problem using coordinate descent methods. And this is a place where it talks about support size. So in terms of last support, so this is the optimum model and the number of non-zeros that you get in the optimum model. As the number of samples increases, the number of non-zeros stay at 25, which makes sense because the probability of selection, of correct selection was 1. And the other guys, Lasso, I don't see where the Lasso is. Lasso is outside probably. L1 relaxed is over here. So they lead to dense models. Okay. Are there any questions?
Let me go back to this higher order swaps, because you're basically searching over a subset of size k. So
Of small size, yes.
yeah. So I mean, can you do 2, 3? Because if you have like 1,000 variables, you have basically you choose.
I agree with you. I'll not hide anything. I agree with you. If you increase the size of k, the complexity is going to blow up. I agree. But, and as a matter of fact, so we actually did experiments to find out, does it actually help? Theoretically, of course, you gain more. But does it actually help? Yes, it does. So for example, if you look at the number of false positives, true positives on a difficult problem, on a difficult instance where, with lots of pairwise correlations, you see if you start adding these swaps, the number of false positives starts reducing. So yes, you gain. Yes. So Lasso is the least squares of the 21st century. So it does the least squares, and then it puts an L1 norm on the regression coefficients. It's a convex proxy to the subset selection problem. So let's talk if you have further questions after the talk. So yes. No, so I'm predicting whether I'm recovering the true beta, sparse beta. I'm generating a model where beta star is sparse. I'm solving my optimization problem, and I'm trying to see if the support that I'm getting matches the support of the underlying probability model. So that's probability of selection. Okay, so now let's talk about the best. Let's ask ourselves a question. We spend a lot of time on trying to optimize best subsets. From a statistical viewpoint, is it really the right problem to solve? Okay. I cooked up a story where I said best subsets is a good thing to solve. Yeah, but is this really the holy grail? So then we come to this. What if the signal to noise ratio is low? So after we wrote our subset selection paper, Hasty, Tipshirani, and Tipshirani, they wrote a paper where they actually did an insightful discussion of the experiments that we did, and then they concluded and they observed that the Lasso outperforms best subset when the signal to noise ratio is low. This was archived in 2017, I think around in August. We were working on this problem parallelly, and 2 weeks just after their paper was released, we uploaded another paper where we said that, sure, if the signal to noise ratio is low, subset selection is bound to overfit. For that, you don't have to look very hard. Just look at this guy. Yi equals to 1 plus epsilon I. I equals to 1 to n. This is my signal. Oh, sorry, let's call it mu I. It's Gaussian sequence model. If the errors are normal, if the noise variance swamps the absolute value of mu i's, of course you cannot do it. It depends upon the signal to noise ratio. So yes, you're right. So in these cases, if the signal to noise ratio is low, then subset selection doesn't make sense. So the question is, okay, what do we do? So let's look at this. So that was a theory example. So let's actually see if that is actually true or not. So we generated a data. We generated a data set where y equals to x beta 0 plus epsilon. X is multivariate Gaussian. Again, same correlation structure as I said over here. Beta is are 0 or 1, and I set the signal to noise ratio to be 1. There is a norm of the signal. and the norm of epsilon are exactly the same. They are 1. And this is what happens to the prediction accuracy. L0 is actually very bad. Low SNR, prediction accuracy error large means it's bad. L1 is pretty good. And guess what's the best? One of the best, L2. This doesn't come as a surprise to people in industry who always use L2. L2 is amazing for low signal optimization. It is magic. So it works extremely well. Now let's look at the number of non-zeros. If you look at the number of non-zeros, L0 detects that there is an overfitting going on. So it tries to mitigate that effect by selecting a sparser model. L1 gets a good prediction model, but it increases the number of non-zero. And this is another method which is known as L1P, L1 polished. So what do we do? So we thought, okay, let's try a very, very simple thing. I'm not a big fan of complex methods. So let's try a simple thing. Let's try taking this criteria. Let's take subset selection and add a shrinkage to it. It's a very simple thing to do, along with subset selection. It's a regularized version of the subset selection. The nice thing is this is a very easy to interpret criteria. I know what is going on. I shrink the regression coefficients, and on top of that, I do subset selection. And you can actually prove theorems about this because this is the solution to an optimization problem. You can exactly explain why is it that the prediction accuracy of subset selection is bad when the sigma, that is a SNR, is low. You can explain why is the prediction accuracy, why is the prediction accuracy of Lasso so good when the SNR is low, and you can also show why this one leads to a better model. Now the implications of this model is interesting because if you do L0 plus L1 and L0 plus L2, look at the prediction accuracy. It now starts matching the best of L1 and L2. There may be a high variance, that's possible because of the L2, but now let's look at the number of non-zeros. If you actually look at the number of non-zeros, you see that these are usually much denser, much sparser than the model given by L1. Okay? And that's dense sparsity you get because of cardinality constraints. I think there is a deeper story over here that we are trying to investigate. This has to do with model aggregation methods that are used in non-parametric statistics. So, but we are investigating it. I don't have a clear picture of it about it yet. What actually happens to these combinatorial optimization methods is the signal to noise ratio is low. Okay, so I think there is a deeper story over here, which would be interesting to understand better, but at the moment we do not. Okay, so how are you doing on time?
Yeah, 6 more minutes, but I think we can take that for questions. Yeah, so 6 more minutes on the clock, but normally we leave a few minutes for questions.
So what should I do?
Yeah.
Okay, good. Half. Perfect. Okay, good. So I'll quickly go over it. So essentially, midpoint estimates are always good.
Be discreet about it.
All right. Okay. So all right. So faster subset selection. Okay. Let's move over this. This is I'll get over this, and then I'll talk a little bit about a problem of a very, very different flavor. So this is a problem on low rank factor analysis. Factor analysis 1905. The model was proposed by Spearman. It's one of the fundamental methods out there. It's a very, very minor modification to the PCA, principal component analysis. The problem is difficult to solve. It's very, very, it's just difficult to solve because of the diagonal stuff that comes in. Surprisingly, there hasn't been any work on this, with the exception of some recent work done in applied math and optimization. I mean, the computational aspects of this. So factor analysis, the way to write it down is a very simple. I write down the covariance matrix sigma. It's essentially a matrix decomposition problem. I write it as a sum of 3 components. This one is the theta. It's essentially the matrix of common factors, as you like to call it. This one is the error, and this one is the error unique variances or uniquenesses, as they call it. So these are the common factors. These are the errors. So this is the part that cannot be explained by the common factors. This is the unique variances, and this is the covariance matrix. So with the exception of these 2 works, this work, Saunderson et al. In 2012, which builds on the work on Tenenberg and Gears, which actually looked at this problem, from an optimization viewpoint, and at least they appreciated the fact that this problem is a difficult problem. And so what are the implications? If you actually use an R package to solve this problem, you may end up variances being negative. These are known as Haywood cases. This happens. If the problem becomes difficult, this happens. So sure, you may say, I don't really care about a fancy algorithm, but deal with the case where the variances are negatives. So what will I do? All right, so we said, okay, so fine. So let's try to set it up as directly as this matrix decomposition problem as a matrix approximation problem. And if you set it up as a matrix approximation problem, it becomes what is known as a rank constraint problem with semi-definite constraints. All right, so it's a nonlinear optimization problem. It's a non-convex optimization problem with semi-definite constraints. So essentially what we try to do in this paper is we take this object. This problem is difficult because of the rank constraint. This is a convex form. So what we do is we get rid of the rank constraint and then do a reformulation. So we do not do any nuclear norm relaxation over here. It's exactly, we just take this problem and then reformulate it as another optimization problem. And the other optimization problem does not have the rank constraint. It is a function of phi with constraints on phi. It does not have any theta in it. It's a reformulation. Okay, so it needs some work from the spectral properties of these functions to get to that reformulation. And if you do it, then it becomes a curious object for which we needed to use bilinear, outer approximations of bilinear forms to actually solve the problem. It's delicate, but I would say this is an important problem, and somehow we found it very curious that this problem becomes quickly very difficult. Okay, but with this approach, we can actually solve it to problems of the size of around 4,000, exactly over here, and there are no negative variances issues. All right, so let me conclude by saying that statisticians are actually very, very good at coming up with estimators of problems. And actually, even if you look at most of the methods that I discussed over here are very old methods lying in textbooks. I'm a big fan of using classical methods. And actually, if you read these old textbooks, you see that there is a lot of intuition in between the lines. All right, best estimators are over there. So essentially, most of the estimators are actually come from natural statistical thinking. But it turns out that often these estimators lead to difficult optimization problems. And in order to approach those problems, what I demonstrated over here is, let's use mathematical optimization techniques to think about solving those problems. Often there is an interplay between this, because some problems are difficult to solve. There is a problem that I didn't have time to talk about, that actually you can probably go to the statistics problem and then change the statistics problem to make it easier. And there is an interesting thing that is happening at the interface, because we're trying to understand what are the good estimators that you can build, and what is the trade-off between statistics and computation. By trade-off, I do not necessarily mean polynomial time versus non-polynomial time. By trade-off, I mean, by computation, I mean, give me a data set, can I actually solve it or not? Do I need to solve Martin's SVM problem in 2 seconds or 1 hour? So those are considerations that are needed. And let's try it out, because there are tools out there to do it for you. Okay, thank you. Sure, I agree.
Estimate they get at the end still depend on the data.
Absolutely, yes.
So so in this case, if you cannot really write down the model and then translate that into the optimization problem, then would that still be possible to do what you do here?
I'm not sure if I completely understood your question, but let me try my shot. So yes, optimizers probably do not care about variances, but I'm not an optimizer. Okay, I'm probably mixed. I don't know. So I'm a statistician. I think this estimator. In order to, let's look at an estimator. Suppose let's look at this estimator, the fundamental Gaussian sequence model estimator. All right, I want to get an estimate for mu. Okay, so how will I do this? I'll try to understand risk properties of mu. inside the risk properties, bias variance trade-off is going to come in. I want to understand the variance of this. I can do, in some cases, I can do theoretical computation. In some cases, I can just simulate it and try to understand this. So the thing is, yes, statistical thinking is always there. I mean, I'm trained as a statistician. I'll think about the statistical aspects of the problem. But the issue is, in order to get an estimator, and in cases I know that this estimator is going to, there are reasons to believe that this estimator cannot be beaten in terms of information due to information theoretic reasons. That estimator somehow is written as a solution to an optimization problem. So that's the place where I use my optimization hat, solve the problem, and then go back. So I'm not saying forget about statistical thinking. No, that's very, very important. I mean, that's honestly why that's at least, that's what got me thinking about these problems. I'll use optimization to solve statistics problems. So yes, that is very important.
Other questions?
Do you ever transform the betas, like sets of them, into like a single X to turn the next step of the problem around?
I'm sorry, I didn't understand.
Yeah. I'd have to explain that a little more. If you are trying to estimate a model
Right.
that has a lot of subsets in it,
Right, right,
each of those subsets could be gotten as an estimate,
right.
but that estimate in turn could be a single beta with a vector of values.
Right, from
for
these
the
subsets. Yes, yes.
So you turn it into a variable.
Right. So the question is, can I use this idea? Have I tried it? No, I haven't, because I don't know. But there are. I don't know whether I have tried exactly this problem, or there are versions of this problem which is known as structured group variable selection, where these groups actually have meanings. There are probably genes corresponding to some genetic pathway, or for example, they correspond to a group of pixels in the human brain. So these problems have been out there. These are structured objects, structured group problems. So we are working on it. We have a draft. We have done some computations on it. We don't have a paper yet released, which actually tries to explore some of those objects, those structures, using these kinds of methods. But again, so the thing is, the problems. So at the moment, we do not have a very, very good understanding about those problems, because we are still trying to understand the simple problem. But yes, you can.
See, I've done things like that with, like, ICD-9 codes, where there were 14,000 codes.
Right.
Take my model and I find out for the subset that corresponds to one of those codes, how much I have to change the intercept parameters.
Right.
Three-dimensional problem, but anyway.
Right.
And then I get that estimate.
Right.
Well, I can turn those estimates into a data set
Uh-huh.
and put it in as a single variable.
Uh-huh. Oh, I see what you're saying.
And then
Yes,
run that.
sure. Yes, you can do it. So that's the place where the data analyst's expertise or the statistician's expertise is going to come in. Yes,
Oh, yeah,
of course.
yeah, I
Yes,
mean,
absolutely.
it's
I agree.
Not your general problem.
I agree. So I would say, so this is actually one thing that I've been realizing. When it comes to very fancy modeling or natural modeling intuition that a statistician derives from his or her data set, there aren't many ways actually how to, I mean, so if you want to include a bunch of these constants, suppose you solve a regression model. You don't like the value of the coefficient. You don't like this parameter. You don't want these two coefficients to stay together. You want to do something to it. So this way of model updating. So one way to do that, I would say one way naturally to do it is by using optimization principles to enforce those constraints. That's essentially how OR people do solve their problems when they're solving their problem in a managerial setting. So I haven't really, I think that's a natural thing to do in, at least one way to attack statistical data analysis problems. I don't know whether I've answered your question.
Okay.
Very good talk, and I don't say that very often.
Okay, thank you.
Do you have any general comments on breaking down research stovepipes that, I mean, you're going to other people in other disciplines finding out information on optimization algorithms that you could apply in your work. And you were telling me in the office that you never had that interaction at Stanford. And
at Columbia. Yeah, so that's why probably, I don't know, how to do it, I don't know. I don't have a recipe. I don't know. That's why people think, that's why some statisticians think I'm an optimizer. so it took, I would say, yeah, it took time. Is there a, right. So I would say, so yeah, so essentially one of the main reasons I got interested in it, or that has been driving a lot of my research, is essentially my colleagues. They are very excited about what they do. I talk to them. They tell me what is out there, what can be done, and what cannot be done. I try to use those methods and then see whether it can be done. Oh, of course, yeah. Of course, yeah. Yes, exactly. So essentially one way to think about it is, okay, I need this problem to be solved, or what are the methods out there to solve this problem? Then they start asking questions. Then they go back. So there is a to and fro. So for example, the high correlation thing, it's an interesting statistical observation, but it also leads to a very difficult optimization problem. So what is actually going on from an optimization viewpoint? That's their questions to answer. I don't have, so yes, there is an exchange over there. Okay, thank you. I'm glad I didn't trip over.
Yeah. I was trying to figure out a way.
No, that's fine. I was being watchful. Thank you.